All right, as promised, here is a few more examples of repeated integration by parts using the tabular method, and I'll have one example of a U-sub integration by parts combo. So first, to make sure you're awake, here's Chester. This is Chester waiting for his bus, which is what we call the minivan that his babysitter Sue pulls up in every day that he goes to see her to pick him up. So he's waiting very excitedly. All right, on to integration. First problem, x squared sine of pi x dx. Your first clue that this is going to be a repeated integration by parts is that you have an x squared, or a polynomial with an exponent greater than 1. So set up your table. We know we need a column for the repeated differentiation and the repeated integration. The differentiation for this one's pretty simple, x squared, 2x, 2, and we stop when we get to 0. The integration, watch out for the pi x, right? That means we have to do a reverse chain rule. So the integral, or actually let's start with sine of pi x. The integral of sine is negative cosine, but we have to multiply that negative cosine by 1 over pi to account for that factor of x. When we do it again, we know the integral of cos is sine. There's already a negative there. We have to multiply by 1 over pi again, so that becomes negative 1 over pi squared sine of pi x. And then if I do it one more time, the integral of sine of pi x is negative cosine, and so that negative goes away. We end up with 1 over pi cubed cos of pi x. Now, you can do your arrows. We know we have to alternate between positive and negative because what would happen, that's what would happen if we distributed that negative, if we did integration by parts more than once. So down here, write out my problem again. And this is, if I multiply everything together, x squared over pi cos of pi x. We have a minus and a minus, so it becomes plus 2x over pi squared sine of pi x plus 2 over pi cubed cos of pi x plus c. And sorry, I forgot that there should be a negative in front of that first term there. All right. So as you're going through and watching this video, maybe pause and try each problem before I do it, and then check my solution to see if you've done it right. That would be a good way to use this for studying. All right, let's look at the next one. Integral of arctan of 4t dt. So we did one similar to this on the first day of integration by parts with just arctan of x. And it's not immediately evident that this needs to be integration by parts because there's only one function that we can see, but this is one of those where we have to rewrite it as 1 times the arctan of 4t. So a little bit of calculus trickery there. So I'm going to let my u be equal to arctan of 4t, my dv be equal to 1, du is 4 over 16t squared plus 1. And that's a bit of a baby chain there, right? We have this 4t inside, so we have to take the derivative of that and multiply it by the derivative of the outer function, which is arctan. My v is going to be equal to t. So now, integral of arctan 4t dt is equal to my u times v, so t arctan of 4t minus the integral of 4t over 16t squared plus 1 dt. And now it doesn't look like we've made much progress here because we have this ugly integral to evaluate, but actually we can do this using a fairly simple integration by substitution. So instead of using a u, because we've already used a u somewhere, I'm going to use an m. And I'm going to say m equals 16t squared plus 1. If I do that, dm becomes 32t dt. And I already have this 4t here, so I have something that looks like this 32t, but I'm off by a factor of 8. And so that's easy to compensate for. I can just rewrite t arctan of 4t minus, I'm going to multiply this whole thing by 1 over 8, and it becomes the integral of 1 over u, 1 over m dm. All right, and we know how to integrate 1 over m or 1 over u or 1 over x, because that is just ln of whatever is in the denominator plus c. And then the final step is to substitute what I let m equal, which was 16t squared plus 1 plus c. You'll notice here that the absolute value signs on 16t squared plus 1 aren't really necessary because it's always going to be a positive number, right? Anything squared plus 1 is always going to be greater than 0. But just keep the absolute value signs there. It's not hurting anything, and it's just a good habit to get into. All right. Next problem. Again, pause. Try to do this one yourself using the tabular method. I think we did this one in class using the regular repeated integration by parts, but test yourself to see if you get the same thing using the tabular method. And I will set up my table over here. I know my derivatives for that. Be careful with your derivative for e to the negative x. That's another little chain rule that we have to do in reverse. So the integral of e to the negative x would be negative e to the negative x. If I take that integral again, the negatives multiply to give me a positive e to the negative x. And then one more time, I end up with e to the negative x again. There are the arrows, plus, minus, plus. So the integral from 0 to ln of 2 of x squared e to the negative x dx is equal to negative x squared e to the negative x minus 2x e to the negative x minus 2e to the negative x from 0 to ln of 2. All right, when I evaluate this in the next step, I'm gonna make all of my e to the negative x's, I'm gonna convert them to 1 over e to the x because I think it will be easier for you to see how I'm evaluating. So first plugging in ln of x, ln of 2, I get negative ln of 2 squared over e to the ln of 2 minus 2 ln of 2 over e to the ln of 2 minus 2 over e to the ln of 2. Minus, I know if I substitute 0 in for my first two terms here for these two, they're just both going to be 0. And so I'm left with minus 2e to the 0. If I evaluate this, remember that e to the ln of anything is just that, anything, right? Because e and ln are inverse functions. And so this term becomes negative ln of 2 squared over 2 minus ln of 2 minus 1. This term, e to the 0 is 1, so I'm left with a negative 2 times a negative, which is a positive 2. And so my final answer for this is negative ln of 2 squared over 2 minus ln of 2 plus 1. All right, and the last problem. I see that I have an e to the 2x and a sine of 3x. So I have an exponential function and a trig function. And so using the tabular method for this one is similar to that problem where that we did in class, where you have to stop the table at the appropriate point, or else you'd just be taking derivatives and integrals forever. So let's set it up. Differentiation and integration. E to the 2x, 2e to the 2x, 4e to the 2x. Now for the sine. Sine of 3x. Watch out for the little chain rule here. Negative 1/3 cos of 3x, and then negative 1/9 sine of 3x. And that's all I need. And you're going to say, how do you know to stop there? I know to stop there because what I have is what I started with. I have the trig function that I started with. And if I were to keep going, I'd end up going cosine every time. You want to stop as soon as you get back to that original trig function. So we know we have those two to multiply by each other, positive, negative. And then this is where it's a little bit different with these. We have to consider those two being multiplied together as well at the end. So the integral of e to the 2x sine of 3x dx is equal to negative e to the 2x over 3 cos of 3x plus 2e to the 2x over 9 sine of 3x. And then be careful here, because we're going straight across, this is like a u dv situation. So we still have to subtract that integral, right? So this is still going to be minus the integral of those two things multiplied together. So it's like you're doing the integration by parts, but the last step. So 4e to the 2x over 9 sine of 3x. Sorry, I'm running out of space here, dx. And then the key to these is that you end up having on the right-hand side something that looks similar to what you have on the left-hand side. What those actually are like terms. So we're going to collect those like terms on one side. And if I do that and I find a common denominator and I add them together, I get 13 over 9 times the integral of e to the 2x sine of 3x. And that is equal to the things that I left on the right-hand side. So plus 2e to the 2x over 9 sine of 3x. Let's add a plus c so we don't forget. And then the key is to isolate that integral. And so we multiply each side by 9 over 13, and we end up with something that actually looks not too bad. So we end up with negative 3e to the 2x cos of 3x over 13 plus 2e to the 2x sine of 3x over 13 plus c. All right, so I hope that helped. Again, go back and try those on your own. And if you have any other questions, you can always come to those extra help sessions. And if you can't come to those, feel free to email me and we'll set up something else.